Roger, Neil. We're reading you loud and clear. Let's see, getting some pictures and the contingency sample.
One of the first things Neil Armstrong did after stepping onto the moon was collect some soil.
Okay, gonna get the contingency sample there, Neil.
From next to the lunar lander.
As you get close to it, it's almost like a powder.
50 years later, here it is, at the Open University in Milton Keynes. So that's quite a piece of history, isn't it, I'm holding there? Don't drop it.
We have to account for every milligram and record it, but then we have to send it back because NASA needs to make sure that all of their samples are accounted for because they can't be sold. These are priceless samples.
In fact, the OU's been testing Apollo moon rock for decades. Incredible as it sounds, in their latest experiment, PhD student Hannah Sargent is turning lunar dust into water. To show us how, she's using NASA's replica soil because the real stuff is so precious. In 5 years' time, thanks to a collaboration between the European Space Agency and the Russians, her experiment could be happening at the south pole of the moon. It's one of the coldest places in our solar system. They'll be heating moon rocks to 5 times the temperature of your oven, so the oxygen inside reacts with hydrogen they've brought along, making H2O. Why do you want to make water out of moon rock?
Yeah, so water is one of the most critical resources we need for space exploration, not just for the life support needs of humans, but also to make rocket fuel. Hydrogen and oxygen is propellant. So if we can produce that on the surface of the moon, we can support long-term space exploration missions and produce the rocket propellant we need to perhaps use the moon as a sort of pit stop for missions on the way to Mars.
I think if we're honest, a lot of people will be surprised the Open University is doing this kind of work with lunar missions and NASA and the European Space Agency and so on.
Yeah, so the Open University actually has a really long heritage of working in space exploration. I just don't think it's well known.
Elsewhere on the campus, an unusual sight. Scientists pushing a moon rover down the road. Slow over the speed bump. This is LoveMe, a prototype of a lightweight, relatively low-cost rover that could one day be driving around the lunar poles. Although for now, they're having to improvise a bit.
The next person to step in anyway, please collect that black thing.
The OU isn't making the rover, but Dr. Simon Sheridan and his team are building a key piece of equipment on board. Put simply, it sniffs gases to find water, and it's called a mass spectrometer. Here's how it works. First, a drill goes 10 to 20 centimetres into the ground.
It's like an upside-down coffee cup with some nasty teeth on the bottom, and then when it's embedded, there's a central heater rod which we turn on, and that sort of puts a thermal heat wave from about 400 or 500 degrees centigrade into the regolith, and any water that's in ice form, it will then volatilize and it will go up the spout into the mass spectrometer, which is this thing on the top here.
For years, scientists lost interest in the moon, assuming it was a barren ball of rock. Then around a decade ago, something very exciting happened. NASA shot a disused rocket stage at 5,500 miles an hour into a dark crater at the lunar South Pole, a place the sun never shines. Amongst the debris spewed out was water ice, crystals stored in a deep freeze, possibly left over from when the moon formed or dumped there by comets or asteroids.
We know there is water on the moon, so all the evidence is pointing there could be quite a lot. We have return samples, we have meteorites, and they all show they contain water. And from orbital data, there's a lot of areas that are showing evidence of water as well. We just don't know how much there is there. So it could be a very, very thin layer of water ice, or it could be a big depth of it. So an instrument like the mass spectrometer and the drill on the LoveMe rover would actually quantify how much is actually there.
Modern space science is so tricky and so pricey, it relies on collaboration. Which is why I've made the trip from Milton Keynes to Cologne in Germany, where the European Space Agency tests its astronauts and entertains big kids who are visiting. Sadly, I'm not training to be an astronaut, but if I was, this is where I would do it. It's an exact replica of the European lab that's currently orbiting the Earth on the International Space Station. And this is where the astronauts go to bed. Good night. In a nearby lab, another OU scientist, Professor Mahesh Anand, is catching up with German colleagues because they're working on the same problem: how to build houses on the moon.
So what you see here is the lunar simulant we are using for our experiments, and we are putting that inside of the solar oven. We come with the solar beam and we go over that layer by layer, line by line. Then we put another layer on top of it, and the end result of that is a brick similar to this one.
It's quite a specialist conversation.
Do we really think that the vesicles that are forming is because of the release of volatiles within the minerals that form the JSC1A?
We've seen an experiment to turn lunar soil into water. This experiment turns the soil into bricks. It's like a giant version of something kids have done for years. They use enormous mirrors to focus the sun into a powerful beam. Sunlight is in plentiful supply across large parts of the moon because, unlike Germany, there are no clouds to get in the way. So luckily it's not sunny today, otherwise we'd be frying. But you can imagine the sun beaming onto those mirrors there, onto these mirrors here, and then up onto that mirror there, getting super hot super quickly.
Exactly, and these mirrors are doing phenomenal job of concentrating that solar power, solar energy to an extent that actually they can fuse that simulated moon dust within a fraction of seconds to maybe a few minutes, where temperatures can reach in excess of 1,000 degrees centigrade.
The sunbeam's only the width of a coin. It's fusing the moon dust together. They then use the material to 3D print bricks. So Mahesh, this is what it's all about. This could be basically a moon brick for a building on the moon.
Exactly, this is it. The point is to demonstrate that actually you can use the concentrated solar energy to fuse simulated moon dust into something solid, which could then be used to kind of make a brick in a layer by layer pattern.
Mahesh and his team are looking at using microwave power for the same job, to work in areas of the moon that never see the sun.
Depending upon the location, exact location on the moon, it may be that actually solar energy might be more useful than the microwave or vice versa. And this is the neat thing about doing internationally collaborative research, that you make progress in no time.
The key to future space travel is learning how to live off the land, turning seemingly barren dust into water, oxygen, rocket fuel and houses, so the moon becomes a filling station for trips to Mars. You might have thought the Open University was just people doing degrees from their bedroom. But when humans are finally living on other worlds, it'll be OU scientists that help get them there.